Okay, let's begin. Today's speaker is Peter Mayr, and he will speak to us about generic automorphisms of Boolean powers.
Thank you. Welcome everybody in here and out there. This is a continuation of some joint work with Nick Hrushkutz from University of St. Andrews, where we studied combinatorial properties of direct powers of finite algebras. I spoke about this last February 24, a year and a half ago. So there is some significant overlap with this talk on PALS. I apologize to you, but there are going to be some new results. And so I'm just going to start at the beginning. The general setup is going to be a review a bit of combinatorial properties of finite direct powers of finite simple Maltsev algebras. Then I'll speak about construction Boolean powers, and finally about automorphism groups of those Boolean powers and some new properties that we figured out about them. So let's start at the beginning, finite direct powers. So just for a review of general algebraic effects. Throughout my talk, A is going to be a finite simple Maltsev algebra. So simple just means that we have exactly two congruences, the total congruence and the equality. A has more than one element also. Maltsev algebra means we have a ternary Maltsev term satisfying these identities m of x, y, y equals x and m of y, y, x. I will mention abelian and non-abelian Maltsev algebras. So in this setting, a Maltsev algebra, think of it as just abelian if its operations are affine operations on some module. It's non-abelian if there are some operations that are not affine. So the canonical examples that you may want to keep in mind for abelian Maltsev algebras are like, I'll be interested in simple algebras, so simple modules, finite simple modules. They are all just essentially determined. You have a finite vector space F. You look at Fn, and you have the full matrix ring Fn times n acting on it. So, but there are other abelian simple Maltsev algebras that are a bit more obscure, if you want, like the one down here. Take the integers modulo p and the Maltsev operation x minus y plus z. And so this satisfies the Maltsev identity. And then you can throw in some other affine functions, like, for example, the translation x goes to x plus 1. So this would give you an abelian algebra. For non-abelian algebras, prime examples are simple non-abelian groups, or quasi-groups or loops, if you want, like A5, for example. And, oops, I didn't want to do that. Or full matrix rings over finite fields, right? N times n matrix ring with addition of multiplication. These are also non-abelian simple Maltsev algebras. Okay, so these are the, you may want to keep this in mind whenever I say simple Maltsev algebras. Now, I'm going to be interested in homomorphisms between finite direct powers of these guys. So, say H is a homomorphism from A to the K into A to the N. If the algebra A is abelian, then these can be characterized. These are essentially just affine functions again. from a to the k into a to the n, if you view it as a module. So you can describe them, all of these homomorphisms. They're determined by some field F. This is essentially the field of endomorphisms on this finite simple Marchev algebra. And then going from a to the k into the a to the n, you can take the input vector x1 up to xk and multiply it with k times n matrix over that field, and then possibly translate it by some constant vector c. So I don't claim that all of these affine maps are homomorphisms. It depends on which structure you have precisely, but every homomorphism is going to be of such a form. So very, very transparent. So this was the abelian case. The non-abelian case, in a sense, is even easier. If A is non-abelian, then every homomorphism from a to the k to a to the n is just can be obtained by scaling the single components of a vector x1 up to xk by some automorphism of the algebra A, or by some endomorphism to a trivial subalgebra of A. So this is a result by Foster and Pixley, Foster-Pixley theorem. Yes. Okay, why am I interested in these homomorphisms? Because I want to consider for finite simple Marchev algebra the class of all finite direct powers, a to the k, and look at its combinatorial properties, so that I claim this class is almost a Freisig class. So the properties that we have to check for that is that we have first joint embedding property, means given two structures in that class, V and W, so these are finite direct powers, I need to find a third element X in that class, also a finite direct power, such that V and W embedding to X. And this is easily done by what I told you about the homomorphisms, what the embeddings between these direct powers look like. We're also interested in amalgamation. Amalgamation property for a class says given two embeddings, U into V and U into W, then I need UVW are all elements in my class, then I need to find a fourth structure X such that V embeds into X and W embeds into X, and this diagram here computes. X is then called the amalgam, right? V and W over X. And it turns out that for these finite direct powers, we always have that as long as A is non-abelian. And in the abelian case, this works. We have amalgamation if the algebra has at least one element subalgebra, trivial subalgebra. So if you maybe paid attention, going back to our examples, so the class of modules or vector spaces, it has amalgamation because we have trivial subalgebra 0. But this weird guy here, CP with this translation operation destroys all singleton subalgebras. So the only subalgebra is CP itself, right? So for this algebra, we would not get amalgamation for its direct powers. Okay. One third thing for Freisig classes is they need to be closed under substructures. This is called the hereditary property. Now, this works for vector spaces, right? For example, but not if A is a simple non-abelian algebra in general, because you get some subalgebras of A that are not powers of A again, right? So this works. You're closed under substructures if and only if all the proper subalgebras of A are all trivial one element. Okay, but at least in the non-abelian case, we always have amalgamation and we always have joint embeddings, not necessarily the hereditary property. So luckily, this is good enough for some generalized version of Freis's theorem to, if you have a countable class of finite structures with joint embedding and amalgamation, then there exists a unique countable so-called Freise limit of that class. So unique up to isomorphism that's defined by following three properties. So this is just generalization of the usual Freise result where we omit the hereditary property, but this is all classically known. And so the first property is that in the classical Freise theory, we want that every finitely generated substructure of the Freise limit is in our class. So the H of D should be the class of finite structures that we start with. We don't have that here. We only have that every finitely generated substructure of D can be embedded into some element of our class K that we start with. So the red items are the things that change. Secondly, the Freise limit D is just a direct limit of the structures in K, so this remains. And thirdly, you usually have homogeneity, that every isomorphism between substructures of the Freise limit, finitely generated substructures of the Freise limit, can be extended globally to an automorphism of the whole structure D. Again, we don't have that here, just isomorphisms between substructures of D that are in our class K that we start with. Those can be extended to automorphisms. So we call D then just homogeneous for elements in K. All right, so this is very nice. This object exists if we start, say, with a finite simple non-abelian Maltsev algebra and take K the class of all finite direct powers of A. But the natural question to me, at least, was like, can we describe this structure somehow explicitly and algebraically? What is this Freise limit exactly? This is the question that I'm okay. I'm gonna answer for you shortly, but before that, I also want to point out some connection to Ramsey theory here. So one can show that this class of finite direct powers of finite simple non-abelian Maltsev algebra is Ramsey. What does that mean? So you may know a Ramsey theory for sets. This is for structures, but a similar idea means that for all natural numbers k, m, and n, there exists a natural number r such that whenever I have any k coloring of copies of a to the m in a to the r, So I have my big structure AR, right? I look at all the substructures isomorphic to AM. I color them with K colors, or I partition them into K sets, any way I want. Then I can find inside of AR, I can find a substructure, intermediate substructure AN, such that all its copies of AR are in the same partition or have the same color. Right? So within that chaos of the coloring of the big structure, I find a nice ordered substructure where every copies of AN have the same color. Okay, so we just observed that fairly recently. I don't know whether anybody else figured that out earlier. It's quite possible. The proof is not hard if you it follows pretty straightforward from the embedding how these substructures sit into each other using the Foster-Pixley theorem, and what's called the Graham-Rothschild theorem, which is kind of the cornerstone of structural Ramsey theory. Right? So it's kind of everything is proved using that. Okay, this is interesting, and maybe it also has some connections to topological dynamics, like Kekres, Pestov, and Todorcevic. 2005, they published a very influential paper where they showed that in this situation where you have such a Ramsey class and a Freise limit, then you can you can put some order on your structures in a natural way and on the Freise limit, and then the automorphism group of that Freise limit with that natural order has some nice topological properties. It is what's called extremely amenable, right? People are interested in this objects, but I don't have time to go into any details here about that. It's just another kind of angle that makes me more interested in what is this Freise limit that has this nice automorphism group. Can we describe it explicitly? Okay, so this was all teasing. Are there any questions so far? Please interrupt me.
Yeah. What if it's not a billion? What if it's a billion?
If it's the question is, what if the structure A is a billion? So it's known that the class of finite vector spaces over a fixed finite field has Ramsey property. Right? Graham and Rothschild proved that actually. For the arbitrary billion Maltsev algebras, I'm not quite sure. Right? So I mean, there's a classification for those, right? But I didn't get to check the details whether this really generalizes. I'm not entirely sure about that. All right. Okay. All these questions and no answers. So I want to talk about the next item on the list, Boolean powers. This is a classical construction. If you haven't seen it before, that's due to, I think, the first Ahrens and Kaplansky in the 40s. So I'll just present it briefly. Let's say A is a finite algebra with, say, just a discrete topology on it, and B be a Boolean algebra with stone space X. So you can think of B is represented on X just by the Klopen subsets on this topological space X. Then we want to look at the subalgebra of the direct power A to the X. subalgebra of a to the x of all functions from x into a that are continuous. So yes, and this is called the set of Boolean. The set of continuous functions forms subalgebra under component-wise operation of the component-wise application of the algebras in A. And this is called the Boolean power of A by B and denoted by A to the B. Right? It's not a set of functions from B into A. It's a set of functions from the Stone space X into A. So this is the Boolean power. So then some definition that we borrowed from set theory, I guess I'll call an element in an algebra A idempotent if it generates a singleton, a trivial subalgebra. Right? Somewhat non-standard, but then for n distinct points, x1 up to xn in the Stone space, and n idempotents or trivial subalgebras of A, I can define the filtered Boolean power as a subalgebra of the Boolean power, a to the x or a to the b, if you will. So these are all the continuous functions from x into a that additionally satisfy the property that at point xi, they take value this idempotent ei, singleton subalgebra, for all I between 1 and n. So this is what I will call a filtered Boolean power. There are some generalizations of that in the literature as well, but this is this will be enough for me. Okay, and now finally, one answer, right? You may have guessed or remembered from my previous talk that for a finite simple Maltsev algebra, if we have amalgamation, so if this algebra is non-abelian or abelian and has a one-element subalgebra, then the generalized Freise limit of finite direct powers of A is just a filtered Boolean power of A by B. What do we have to filter by? Well, by the complete set of idempotents or trivial subalgebras of A. So say A has n subalgebras, and we can pick arbitrary n points. I forgot to mention, it's the Boolean power of A by the countable atomless Boolean algebra, right? Whose Stone space is 2 to the omega. It's just the counter space that I think most of you will know. So you just counter space is homogeneous, so you just pick any n distinct points and filter the functions at those 2 points to the full set of idempotents of the algebra. Okay, how do you prove that? As always, you just have this this filtered Boolean power, the description of this object, and you have to check that it satisfies the defining property of the Freise limit, which was like, I don't know, finitely generated substructures are all can all be embedded into finite direct powers of A. This Boolean power is the direct limit of finite direct powers, and we have homogeneity in this Boolean power with respect to substructures that are finite direct powers of A. So this everything is easy except for the last one. This is a bit annoying to work out, but it's also not hard. Okay. So the Freise limit is a Boolean power. One bonus thing, so this is just, what do you call it? an advertisement for Boolean powers, I guess, this talk. There's a beautiful result of McIntyre and Rosenstein where they characterize omega categorical Boolean powers. So okay, countable structure is omega categorical if it's the unique countable model of its own theory, right, up to isomorphism. And in our setting for a finite algebra and all these filtered Boolean powers, they are going to be omega categorical. So the Freise limits, those that I construct as Freise limits will be because of Freise theory, but yeah, what this says is the others are omega categorical. So, okay, so some bonus information, maybe more than you wanted about Boolean powers. So next, I want to talk about the automorphism group of my Freise limit of this Boolean power, and about its combinatorial and topological properties. So for this, again, first general setup, general definition for any countable infinite structure M, say, you can look at its automorphism group, let's call it G. And then there's a natural topology on this automorphism group. It's called topology of pointwise conversions, where the basic open sets are just stabilizers of finitely many points in structure, and their translates, their cosets, right, in that group. And so this is a beautiful topology. It's Polish as well. Completely metrizable, separable, as good as it can get. Now, yeah. I will call an n-tuple of elements in such an automorphism group generic if its orbit under conjugation by the group G is essentially all of G to the n, right? So this is kind of the intuition for generic elements. They cover all of the orbit under conjugation. They cover all of Gn, essentially. So to make this precise, the action that we consider here is I'll take an n-tuple, h1 up to hn, and then I let little g, act on it in every component the same way, right? So this is a diagonal conjugation action. And the orbit under this action should be real big in G to the n. What does real big mean? In topological terms, it's co-meager. Right? So this means that it contains the intersection of countably many dense open subsets of G to the n. Again, under this broader topology of pointwise convergence on G to the n. So in this setting, this means in particular this orbit is dense in G to the n. So these are generic n-tuples for a fixed natural number n. And then if a group has really a lot of, I call it a group group is said to have ample generics, so a really lot of generics, if it has generic n tuples for every natural number. Okay, so this is, if you've seen this the first time, right, this is just an awful technical condition. But the idea is it connects the topological property of the group with algebraic property, like the conjugation action of the group. And it has some, I don't know what generic tuples are good for, but they have some on their own, but they have some really nice consequences. So this is Kekres and Rosenthal, I think, coined the term, maybe, or defined this notion of genericity that I just defined. And they showed in their paper that assume that an automorphism group of a countable structure has ample generics, so generic n tuples for every natural number n, then this group has what's called a small index property. What does that mean? It means that every subgroup of small index, of index less than 2 to the Aleph 0, is open in that topology. So remember, open sets, basic open sets were just stabilizers of finitely many points. So this means that every subgroup of index less than 2 to the Aleph 0 contains the stabilizer of finitely many points. So this is what the small index property says, and the group permutation group may or may not have that. But ample generics imply this. So clearly, clearly every stabilizer of finitely many points in a permutation group is gonna have small index of index less than 2 to the Aleph 0, if it's a permutation group on a countable set. Small index property says something like the converse holds as well. Every small index subgroup contains a point stabilizer. And it has some interesting consequences. Again, connecting the topological and the algebraic structure of the Polish group G. Right? So a small index property implies that every homomorphism from G into some other Polish group, every group homomorphism is automatically continuous. Right? So you get automatic continuity from small index property, and it also implies that there's a unique Polish topology on that group G. Right? So namely this pointwise convergence, and there's no other way to put the Polish topology on it. Okay, so this is one thing that we can prove with ample generics. And the next, if the automorphism group of M has ample generics, and additionally M is omega categorical, then this automorphism group also has what's called uncountable cofinality. Meaning that G cannot be obtained as a countable union or of a chain of proper subgroups. So this is just maybe to think about it like a condition that says the group is really big, right? So you can't approximate it, you can't get it as a countable union of a chain, ascending chain of proper subgroups. Uncountable cofinality. And one more thing, Bergman property says that for any generating set of that group, satisfying some technical conditions, like that the generating set for every element E generating set E contains for each element also its inverse, and it contains the identity element. So then there exists a natural number K such that the group elements of the group can be written as a product of K generators. Exactly. Yeah. So this is again is a condition on size, if you want. And the generating set E essentially is as big as G already, right? So you get the group elements just by products of fixed finite lengths of elements. Okay, so these are properties that have been studied for permutation groups classically for the last 40 years in model theory, topological dynamics, permutation group theory. They have been established for many classical permutation groups. This is just a tiny overview of results that are out there. No need to go through all these results. Just say if you take as your structure the natural numbers with no relations, no operation on it, right? So then the automorphism group would just be the symmetric group on for bijections on N. And people have proved SIP, small index property, uncountable cofinality, and Bergman property throughout the decades. And then 2007, Kekres and Rosenthal kind of subsumed all of these results using their approach of ample generics. And this is the way it usually went. However, I just want to point out that just because a group has all these properties, all the three consequences of ample generics, it doesn't need to have ample generics itself, like dense linear order Q with without endpoints Q less than. It doesn't have any generic pairs, so no generic two tuples. So most of the results that are out there on ample generics and these other properties concern automorphism groups of homogeneous relational structures, or homeomorphism groups of topological spaces, or automorphism groups of spaces with some bilinear form, right? So result like that. Very few are there about algebraic structures. So just want to point out vector spaces over finite field, right? They have all these properties. As far as I know, ample generics is open in this sense. Let me go back to that. And another outlier is like 2 to the omega, if you remember, is the Cantor space. The homeomorphism group of the Cantor space is the same as the automorphism group of the atomless Boolean algebra, B. And Kwiatkowska 2012 showed that this group has ample generics as well. So where are we at? We are at the bottom of this pile, and I mentioned like 1 or 2 years ago in this seminar that for filtered Boolean powers of A, finite simple non-abelian Maltsev algebra, B, the atomless Boolean algebra, every filtered Boolean power its automorphism group has small index property, uncountable cofinality, and Bergman property, and then posed the question, does it have ample generics? We didn't know then, but yes, now we are 2 years smarter. We know it now. Right? We proved that this summer, and this kind of subsumes our previous results. So, yeah, the last 10 minutes or so, maybe. So this is our main result that I wanted to tell you, right? This filter Boolean powers have ample generics, and I just want spend a bit about describing the proof strategy. So I already mentioned that automorphisms of a Boolean algebra B correspond to the homeomorphisms, which are the continuous bijective maps on the stone space of B, X, say. We have this well-known isomorphism. So, and already 2 years ago, we had this result that for a finite simple non-abelian Maltsev algebra and B, the countable atomless Boolean algebra, let's 2 to the omega denote the counter space again. Then the automorphism group of such a filtered Boolean power splits as a semi-direct product of some normal subgroup N with the stabilizer of the homeomorphism group of the counter space to the omega, stabilizing the points x1 up to xn that we use for filtering. Okay, so we have this semi-direct decomposition of the automorphism. Very good. And now we want to show, that this automorphism group has ample generics, right? And as a first step, we're going to show that this pointwise stabilizer has that property, that has ample generics. So that's on this slide. Kwiatkowska showed that the full homeomorphism group has ample generics, but we need it for the pointwise stabilizer. So this is essentially Kwiatkowska's result, but we added the red bits in. And by essentially just following the blueprint of the proof and extending it, so it's not a direct consequence of her result, but going through her proof and extending it at several places to make it work for the stabilizer. So the basic idea is you need to show that you have, for every natural number m, you have a generic m tuple, and so again, this means if you remember that the orbit under diagonal conjugation is gonna be co-meager. Right? How do you get such a thing, or how do you construct it? You can get it as what's called a projective Freisel limit, right? So this is kind of the dual thing to the Freisel limit that I explained before and was developed by Erwin and Suletsky. So this theory, it turns out such a generic tuple can be obtained as a projective Freisel limit of a certain class of finite topological structures on some finite sets A with some binary relations S1 to Sm that satisfy certain properties technically, and I don't want to explain. And together with, if we want to stabilize endpoints, we want to put in n constants in our relational language. So then this you define an appropriate class of such structures, and then the projective Freise limit of that is going to be a structure whose universe is the Cantor space and whose binary relations turn out to be homeomorphisms of the Cantor space that fix these points x1 up to xn. Yeah? So they are in our stabilizer. And the tuple is going to be generic, right? Among all things. It's great. So you can think of this finite structures as kind of some finite approximation of this structure, the Cantor space, with these automorphisms and with these fixed by these points. Okay, so this is very high-level, hand-wavy description of in our write-up currently. This is 10 pages of awful combinatorics and on finite structures, right? But Nick loves that kind of stuff, so it was great for me, right, to have him on as a partner on this. This gives us that the stabilizer of the homeomorphism group has ample generics. Good. And then our main result, that the full automorphism group of filtered Boolean power for A, a finite simple non-abelian Maltsev algebra, and B, the countable atomless Boolean algebra, has ample generics as well. So how to do that? So remember, I mentioned that this automorphism group has this semi-direct decomposition in some normal subgroup. I didn't explain what it was, and the complement, which was a pointwise stabilizer. So then it turns out, by the theorem that we just discussed, we know that we have a generic tuple in the complement for the complement H to M. So let boldface H be such a generic M tuple in H to the M. And luckily, this H is going to be an element in G to the M as well. And luckily, it's going to be generic for that group G as well. We only have to prove it. So these are the next few steps. The main lemma that goes into that is that whenever we take some translate, we take this generic tuple H and we translate it by some M tuple in the normal subgroup N over the normal subgroup N, sorry, then get this A times H. There exists a single element in N such that H conjugated by C using this diagonal conjugation again, so conjugated in the same way in every component, is equal to AH. So again, I think now 5 pages of awful combinatorics and with projective Freise limits necessary for that. But from this, it's not hard to show that the orbit H to the G is just the orbit H to the H with all possible translations by elements in N to the M. And then it's more or less immediate that this orbit H to the G is dense and intersection of countably many open subsets of G. Excuse me. So this is really H is going to be a generic element, a generic tuple in G to the M. Okay, so this is brief sketch of the proof. I'm gonna leave you with some open questions. I posted those these questions last time already. So for the maybe just pass on to the more interesting maybe abelian setting. Just want to mention this. So say A is for simplicity of notation, A is a finite one-dimensional vector space over a finite field, right? And B the countable atomless Boolean algebra. Then from what I said is A to the K is gonna have amalgamation. So we have a Freise limit, which turns out to be I said it's going to be the filtered Boolean power of A to the B by the one element subalgebra, but in this case, it turns out to be just isomorphic to the Boolean power A to the B without any filtering necessary. And this is just a vector space of countable dimension over that finite field. So there's only one of those, right? So yeah. So this is this vector space. You can look at its automorphism group. So this would just be the general linear group for that vector space. Like I said before, it has all these nice properties with individual proofs for small index property, uncountable cofinality, Bergman property. It even has something, a notion that Hodges, Hodkinson, Lasker, and Shiller invented in the 90s. It's called BV generics, which I'm also not going to explain today, but somehow related to the generics due to Kekris and Rosendahl. But as far as I know, it's still an open question whether this general linear group has ample generics in the sense that I defined. So, okay, thank you for your attention. I'll leave you with this.